In this video lesson, we are going to study the steps in SN2 reaction mechanism in halogenoalkanes. SN2 reaction mechanisms in halogenoalkane. So the first thing is, in our previous video on SN1 mechanism, as I told you, SN, S stands for substitution, N stands for nucleophilic, and the 2 there stands for the reacting species or the number of reactants that are involved in the rate determining step. As I earlier said, if it is SN1, it means only one reacting species is involved at the rate determining step, that is at the slow step. But since we are now studying SN2 reaction mechanism, I said S stands for substitution, N stands for nucleophilic, and 2 stands for bimolecular. Bi means there are 2 reacting species that are involved in the rate determining step. There are 2 reacting species involved in the rate determining step. So now, in SN2 mechanism, contrary to what we saw in SN1, only primary or secondary halogenoalkanes can undergo SN2 mechanism. Only primary or secondary halogenoalkanes will undergo SN2 mechanism. In SN2 mechanism, 2 reactants, 2 reacting species are involved. We have the nucleophile and the what? And the halide attached to what? To the alkane. There are 2 reactants. There are 2 reacting species involved in the rate determining step when it has to do with what? SN2. In this SN2 mechanism, it should be remembered that there's only one, the reaction takes place only at the same time. There is bond formation with the nucleophile to form an intermediate. There's bond formation between the nucleophile and the halogenoalkane to form an intermediate. At the same time, the bond between the halogenoalkane is being formed with the nucleophile, there is a heterolytic bond breaking with the halide. All these are taking place at the same time. When the halide finally breaks off, the nucleophile replaces it. When the halide finally breaks off, the nucleophile substitutes it. Once more, there is no carbocation formation when it has to do with SN2. A recap: SN2 mechanism means substitution, means nucleophilic substitution bimolecular, implying that there are 2 reactants or reacting species involved in the rate determining step. Number 2, SN2 mechanism can only go with primary or secondary halogenoalkanes. And number 3, during this SN2 mechanism, there is bond formation with the nucleophile, and at the same time there is heterolytic fission or bond breaking with the halide. Immediately the halide leaves, the nucleophile takes the position. All these are happening at the same time. But it should be remembered that with SN2 mechanism, there is no carbocation formation. There is no carbocation formation when it has to do with a SN2 mechanism. In this reaction, as I said, this is a one-step reaction. Let me put it here. SN2 SN2 mechanism, it is a one-step reaction. Only one step. Only one step reaction. Why I say only one step reaction? Because bond formation with the nucleophile and the heterolytic bond breaking with the halogen takes place at the same time. So it is only one step reaction. 2, the nucleophile approaches the primary halogenoalkane from the opposite side of the bromine. 2, nucleophile attacks from the opposite end of bromine. It attacks from the opposite end of the bromine. See what I am talking of. In this mechanism, we have carbon and bromine. Let's say this hydrogen or something like that. Anything like that. We can say this area. So what happens is this is a polar molecule. So what I am in fact saying is that the nucleophile approaches the primary halogenoalkane from the opposite side. That's why I said nucleophile attacks from the opposite end of the bromine. This is bromine. The opposite side of bromine is this one. So what happened with the nucleophile? The nucleophile will have to attack but from this end. The nucleophile with a lone pair of electron nucleophile will have to do what? The nucleophile will have to attack but from this end. The nucleophile is attacking but from the opposite side. The nucleophile is attacking from the opposite side because of what? The opposite side of bromine because of what? The opposite side of bromine is not clustered. It is not bulky with alkyl groups, because in SN1 mechanism, where we had tertiary halogenoalkane, there were three methyl groups here. There were three methyl groups on the opposite end. So those ones were making the opposite end of bromine to be what? To be more bulky, to be more clustered with the methyl groups. And by doing that, they prevent the attack from behind. There's no space for the nucleophile to enter, so it blocks it. But with SN2 mechanism, where you have to involve a primary or a secondary halogenoalkane, there is space. The opposite end is not bulky. There are not many alkyl groups on the opposite side of bromine, so they attack but from behind here. They have that opportunity to attack but from behind. Number 3. Number 3. The partial negative bromine will do what? It hinders the attack from its side. You know, when a nucleophile is coming from this end, nucleophile is electron rich. It cannot attack from the side of bromine because the partial negative bromine will repel the nucleophile. That's another reason. It will repel or it will hinder the attack from its side. So number 3 will be the partial negative bromine this one hinders or repel attack from its side. Repels attack from repel attack. It will repel attack from its side. So the nucleophile cannot attack from the side of bromine because they will repel it. Like charges will repel, so it will repel the nucleophile. So nucleophile will have opportunity to attack, but only from this side, and will only attack from this side provided the opposite end has no many alkyl groups. Number 4. I said the opposite side is not bulky. The opposite side of the halogen is not bulky or is not clustered. The opposite side of the halogen is not bulky or let's say clustered. It's not clustered with alkyl groups. What I mean here is this. On the opposite side of bromine, on this carbon, on the carbon holding the bromine, there are not many alkyl groups there. There are not many alkyl groups attached to the carbon holding the bromine. For that reason, there is space here. There is space on the opposite side for the nucleophile to enter, to attack. So the opposite side is not bulky. Then the last one, number 5. Number 5 will be the inductive effect of the alkyl group. inductive effect of the alkyl group, the inductive effect of the alkyl group, the inductive effect of the alkyl group on the carbon atom, having the halogen makes the molecule relatively unstable. Why I say it is unstable? Here, there's on this on the carbon having the bromine, there is only one alkyl group there, and that one alkyl group has only little inductive effect. It has only little inductive effect on the positive carbon. You know that alkyl groups are electron donating. When they donate electron on the positive carbon, they help to reduce the charge density on the carbon, thereby making it energetically stable. But because there's only one here, it makes the molecule relatively unstable, resulting in a high activation energy of the reaction. So inductive effect of the alkyl group result in, let me just summarize, result in high activation energy. High activation energy. So, a recap of this one. I said in SN2 mechanism, only one, this mechanism undergoes is only one step. There's only one step in this mechanism. Why I said there's only one step in this mechanism? Because bond formation with the nucleophile and the heterolytic bond breaking with the halogen takes place at the same time. Then number two, I said the nucleophile will attack in SN2 mechanism. The nucleophile will attack but from behind. It will attack from behind or from the opposite side of the halogen. Then I gave reason that it will attack but from behind because the opposite side of bromine where the nucleophile will attack is not clustered. It is not bulky. Number two, it will only attack from this side, from the opposite side, because if it comes through bromine, bromine will repel the attack from its side. The partial negative bromine will repel if it is coming from this side. So it will only have to attack but from the opposite side. Then I said that because of the inductive effect of the alkyl group, there's only one alkyl group there. So little of the electrons are being donated. There's still high charge density on the carbon. There's no reduction in the charge density because only one alkyl group is involved. For that reason, the molecule is relatively unstable. And if it is relatively unstable, what happens? It results in what? It results in high activation energy of the reaction. So now, this SN2 mechanism, our example today will be using bromoethane with aqueous sodium hydroxide. Bromoethane and aqueous sodium hydroxide. Bromoethane and aqueous sodium hydroxide. We are going to use bromoethane here, bromoethane and aqueous sodium hydroxide. We will do what? This is heated under reflux and alcohol results. This is a primary halogenoalkane. when we reacted with aqueous sodium hydroxide, heated under reflux, the hydroxide ion in the sodium hydroxide, in the course of the reaction, will replace the halogen and result in an alcohol. You will see how the whole thing is going. And remember, we said it's only one-step mechanism. So, once more, I said, when bromoethane, which is our reagent, when bromoethane is heated under reflux with sodium hydroxide in a solvent of aqueous ethanol, in a solvent of aqueous ethanol, bromine is substituted by the hydroxyl group and ethanol is formed. Let's do it. Let's do it. Let me write the mechanism so you can better understand what is happening. This is what is happening there. There is a carbon here. There is a carbon, bromoethane. There is a CH3. There is a hydrogen. There is still another hydrogen here. Now, the nucleophile now comes in. I said because there is space here, this area is not bulky, is not clustered with alkyl groups. There is room for the nucleophile to attack, but from this side. So this is the nucleophile, the hydroxide, remember, it's a polar molecule, partial positive carbon, and a partial negative bromine. What happens? I said it is a one-step reaction in which this is the transition state that I'm trying to form like this. That's the transition state. We have another hydrogen here. Remember, there was a methyl group here. was a methyl group there. This is a transition state. In this transition state, you will have remember I said the nucleophile attacks but from the opposite side of the bromine. For that reason, this is the nucleophile. The nucleophile is attacking from the opposite side. We call this state the transition state. Put it in blue. Transition state or an intermediate. It's a transition state. You can call it intermediate. Now, see what is happening here. See what happens here. The result of this is this compound that is being formed. The result of this is the carbon. The carbon. What happens? Bromine breaks off. There's rearrangement in the bond. So there is the methyl group is there. The halogen is the bromine is here. The hydrogen is here. Bromine goes off, the one comes here. Adjustment of position. The hydrogen. And an O. And an O that is from there. Plus the bromide, which is we call it the leaving group, plus the bromide ion with its 2 electrons. The bromide ion with its 2 electrons. That is what happens. That is what is happening there. You will see that here, as I said, you will see that the carbon bromine bond is in this bromoethane. In this bromoethane is polarized because of the difference in electronegativity. The nucleophile is attracted to the partial positive carbon. This is the partial positive carbon. By doing it, it is doing what? It is trying to donate the pair of electrons here. Then, the partial negative bromine is doing what? As the nucleophile is approaching from the opposite of this bromine here, as it is approaching the partial positive carbon to give a lone pair of electrons here, or a lone pair of electron here, what happened? It is at the same time repelling, pushing the bonding electrons in between the carbon and bromine towards the bromine. So it is at the same time repelling repelling the bromine further away from this carbon. But remember, as this thing is approaching here, or as it is approaching at the same time, trying to form a bond with carbon, bromine too at the same time is trying to what? Is trying to split. So the attachment and the splitting are taking place at the same time. Eventually, as they are taking place at the same time, we call this a transition state. We call it a transition state where the carbon bromine bond is just at the point of breaking, while the carbon nucleophile or the carbon OH bond is just at the point of formation. And within the transition state, there are how many groups? We have 1, 2, 3, 4, 5. There are 5 groups within the transition state. It is an intermediate stage. Within this stage, there's rearrangement of bonds. Bonds are formed, bonds are broken, and bonds are rearranged. The mechanism will go on like this. It will go on until the nucleophile firmly attach itself to the carbon, and the bromine finally breaks off. And the bromine finally breaks off heterolytically and go away with its lone pair of electrons. So the mechanism will go on like that until the nucleophile finally attaches itself here firmly. And at that same time, the bromine finally breaks off and go as a living group with its lone pair of electrons. By doing like that, the nucleophile, which is the hydroxyl group here, does what? It has finally substituted the bromine, and that's why we call it substitution with hydroxide ion. And when it finally substitutes the bromine, when the bromine breaks off, what happened? It results in this molecule. It results in this molecule here. And alcohol is the product. And alcohol is the product of it. So that is how this one it goes. And this reaction can be summarized in this form. This reaction can be summarized in this form. We can summarize it in this form like this. As the nucleophile approaches from the opposite side of bromine, it's doing what? At the same time, repelling the bromine and the bonding electron towards the bromine. So there is attachment going on. At the same time, there is what? There is breakage also going on. And that's why we say it is a one-step mechanism. This is the transition state. The nucleophile is at the point of firmly attaching itself to carbon, and the bromine is at the point of finally detaching itself from the carbon. And when it happens, there's a rearrangement of bonds, and this will be the final product. Ethanol will be our product. Then the bromide ion with a lone pair of electrons is left there. So learners, try to understand this. It's a single step and has a transition state. And remember, there is no carbocation formation in this SN1 and in this SN2 mechanism that we are treating here. Our next one will be substituting with ammonia. Substituting with ammonia. Substitution with ammonia. We are done with bromoethane with aqueous sodium hydroxide to form ethanol. Now, substituting with our next example, we're substituting with ammonium. Substituting with ammonium, as you know, substituting with ammonium, you know that this is a primary amine. This is a primary halogenoalkane, the bromoethane that we are going to use. So our reagent in this substitution with ammonia is excess ammonia. Excess ammonia is always needed because it's a lengthy process. Excess ammonia in ethanol. This reaction is heated in a sealed tube, and this result in what? A result in an amine. A result in an amine. So when ethanolic ammonia is heated with bromoethane in a sealed tube, the bromine is substituted by an amine group. The reaction occurs in two stages. This reaction, even though is a primary halogenoalkane, that is bromoethane is a primary halogenoalkane. It goes through two stages. The first step is the formation of a salt, and the second step is the formation of the amine, the amine. So let me show you how it goes. Now, this is our molecule, bromoethane. Step number one. Step number one, formation of ethyl ammonium bromide. Because when bromine with ammonia, it is ethyl ammonium bromide. Formation of ethyl ammonium bromide salt. And this is how it is CH3. Let me write in the equation form. CH3, CH2, that's bromoethane plus ammonia. Gives CH3, CH2, N3. It's a salt there. It's an ionic salt. Then, under stage one, this is the, let me write it. I'll show you how the mechanism is going. Stage one has to do with there is a bromoethane. This is bromoethane. H, I think S3. Yeah. This is bromoethane. Now, when it is heated, when ethanolic ammonia is heated with bromoethane, let me put ammonia here. If ammonia is heated, this is ammonia. This is ammonium, H3N. Remember, in our last video, I told you this ammonia is acting as a nucleophile. Why? Some nucleophiles must not have negative charge, but they have what? A lone pair of electrons to donate. It's a molecule having a lone pair of electrons. Just as like water has a lone pair of electrons. So all of them having lone pair of electrons can act as nucleophiles. Okay. Now, remember this molecule is polar. Carbon, partial positive, partial negative. So what happens? There is attack from behind, as we have been saying. SN2, the attack from behind. There's an attack here. That's an attack by the nucleophile. And that results in what? It results in this salt being formed here. It results in let me just replace the molecule H3 carbon here. Here, the ammonia here has a positive charge. So that is the result of the attack. The nucleophile attacks from behind. The ammonia attack donating what? Donating its electron, a lone pair of electron here. As the nucleophile is attacking from behind, what happens? As a result of the polarity here, there's what we call heterolytic fission. There is heterolytic fission. There is heterolytic fission. The lone with bromine going away with a lone pair of electrons. So these electrons here from the ammonia on the nitrogen are donated to this, to the positively charged carbon, and this is the bond that is formed. Step 2. Step 2. This is step number 2. Step 2, what happened in step 2? What happened in step 2? In step 2, there is formation of ethylamine. Formation of ethylamine. Formation of ethylamine. There is formation of ethylamine. Here, what happens here? Here, a reversible reaction occurs. A reversible reaction occurs between the salt and the excess ammonia. I told you ammonia must be in excess. There is formation of ethylamine, which is what? Which is a primary amine. A primary amine. It's a primary amine. Remember that we do this, but in a sealed, we don't do it using a reflux. A reflux process cannot be used in this process here because the ammonia will escape as gas. A reflux process cannot be used here because the ammonia will escape into the air as gas. So that is why it is more preferable to use but this one, to use but a sealed tube. So under this, let me write the equation so that you see what is happening. Formation of ethylamine. Ethylamine is CH bromoethane, CH2. This molecule here, yeah. The molecule here, NH3 plus, use a plus there. Yeah. Yeah. Plus the ammonium. Plus the ammonia will give what? Will give CH3, CH2, NH, NH2, NH4Br, tetrahydroborate. Okay, now that will be our product in the chemical equation. But let me see how you can better understand it by presenting it in the mechanism way. How the mechanism goes. It will be like this. It will be H3, the carbon, this other carbon, the hydrogen to this, yeah, NH2 plus it is NH2 because the other hydrogen is below here. It is NH2, not NH3 here because the other hydrogen is below here. So do not be confused. This is the other hydrogen. It is NH3. So this hydrogen plus these other two hydrogen will give us NH3. So now plus now the nucleophile again, excess ammonia comes in now. This is excess ammonia. Excess ammonia comes in here with its lone pair of electron on the nitrogen as usual. And what happens? See what is happening? Remember that as the ammonia is attacking this positive charge here, as the ammonia is attacking this positive charge here, what happens? Remember the electrons on the nitrogen here are all here. When it's attacking the positive charge here, electrons, the bonding electrons on the nitrogen hydrogen here are pulled towards the nitrogen. So this is what happens. Electrons here now do what? They now come but here. As attacking this nitrogen, remember this nitrogen is also here. So as the nucleophile is attacking the positive center here, electrons between the nitrogen hydrogen bond are pulled towards the nitrogen, and it is indicated by the movement of the curly arrow. So what happened? This is the resultant. This is the product that results from them. The product that results from them will be H3, the carbon, to the carbon, hydrogen, NH2, and the hydrogen. Plus what? Plus the NH4. That is what happens. Once more, in step 2, formation of ethylamine. In the formation of ethylamine, the nucleophile will do what? Is attracted to the positive center here. As the nucleophile is approaching the positive center here, this hydrogen is in this positive center. As the nucleophile is approaching the positive center here, electrons in one of the hydrogen are being repelled towards the nitrogen. And this result in what? It result in heterolytic fission. A result in heterolytic fission. With the hydrogen going without electrons. And the hydrogen, a result in heterolytic fission. Electrons in this bond are taken by to nitrogen. The electrons in this bond here move but to are repelled, and they move but towards nitrogen. And there's heterolytic fission here, with hydrogen splitting off with no electrons. And nitrogen only benefits from this electron by attaching itself here. When it attaches itself to this lone pair of electrons of this ammonia, what will be formed? This is the NH4 that is formed. The NH4 plus the bromide that left here. The bromide that left in the first case here. That is it. The bromide is still in solution. So that is the whole thing. Step number 1, a recap. Formation of ethyl ammonium bromide salt. Ethyl ammonium bromide salt. As we said, polarity of the carbon bromine bond does what? This is a primary halogenoalkane. Attack is from behind. When the nucleophile attacks from behind, electrons in the nucleophile here are now doing what? Are repelling the bonding electrons here towards bromine. Heterolytic fission again too. The bromine goes out as a bromide ion with a lone pair of electrons. And now what happens? The ammonia attaches itself here. Now this is it with a positive charge. The bromide ion is still there. The molecule comes down here. So it is excess ammonia. Ammonia is in excess. Ammonia is in excess. Ammonia now does what again? Keep on attacking it again. The positive center that was formed. As it is attacking the positive center that was formed, electrons in one of the hydrogen are repelled towards the nitrogen. And this also results in what? It results in heterolytic fission. Nitrogen takes all the electrons, but hydrogen goes like that with no electron. For that reason, it benefits from the lone pair of electron of the ammonia, forming this compound here, forming this compound. And as I said, the bromide that was still in solution combined with it to form this compound. And a new compound there is formed. We call it ethylamine. The new compound is ethylamine. That is the new compound that is formed. Ethyl that is our new compound that is formed. So this is how the reaction goes when it has to do with SN2. A recap of our SN2 mechanism. I said the SN2 mechanism in halogenoalkane involves what? It involves the primary or the secondary halogenoalkane. Only them can undergo SN2. So in SN2 again, I said it is nucleophilic substitution bimolecular. Why? Two reacting species are involved in the rate determining step. Then again, in this same reaction, there is bond formation, and there is also bond formation with the nucleophile, and the heterolytic bond breaking with the halide. We saw it here. An example of the primary halogenoalkane we took was bromoethane with ethanol. Okay, we said this is being heated under reflux, and in the course of heating it, the hydroxide that results from dissociation of the sodium hydroxide will do what? Will act as a nucleophile. Here, it is a one-step reaction. Why I say it's a one-step reaction? The nucleophile is approaching from the opposite side of the halogen. Why? Because it is not clustered. As it is approaching from the opposite side of this one, what happens? As it is approaching from the opposite side of this one, at the same time, there is a bond formation. There is bond formation as it is approaching from the opposite side. There's bond formation. Oh, thank you. I've just realized it now. As approaching from this side, there is bond formation with the carbon, the positive carbon. Nucleophile at the same time have to repel electrons here towards the bromine. Oh, I did not indicate it. I'm sorry. So electrons now move towards the partial negative bromine. Now, a transition in the course of this, there is a subsequent transition state that will develop. In that subsequent transition state, the hydroxide it gets to a point that the hydroxide is about attaching itself firmly to the carbon. It also gets to a point that the bromine is about detaching itself from the carbon. And with other three groups that were there, makes a total of 5 groups that are at the transition stage. This is a temporal stage. We call it an intermediate. In this stage, there's bond formation, there's bond breaking, and there's rearrangement of bonds. After that, what happens? When the nucleophile, the OH firmly attaches itself to this bond, and the bromine finally leaves as a bromide ion with a lone pair of electrons. What happens? An alcohol by name ethanol is produced. An alcohol by name ethanol is produced. This compound again could still, this is the compound CH3, CH2, so this compound results I said the compound can be represented in this way. Examiners would like to put it in this way. Learners, the curly arrows are very, very important. Each step, what is happening at the transition state, what is happening at the initial state here, how many molecules are involved in this molecule here. There are two. The nucleophile and the bromide ion that is also the bromine that is also there. These are reacting species. So there are two molecules. We call it bimolecular. Nucleophilic substitution bimolecular. It's an SN2 mechanism. And it results in ethanol that is being produced. And the bromide that leaves with its lone pair of electrons. It took us again to our second example. Our second example was the formation of a primary amine. And our example was substitution with ammonia. We had excess ammonia, and this is done but in a sealed tube, but not in a reflux. So the same procedure, but in this case, it is a two-step, irrespective of the fact that it is a primary halogenoalkane. A two-step process occurred here. There was ionization with bromine leaving and the ammonia attaching itself. Secondly, formation of ethylamine, which is a primary amine. The condition, ammonia must be in excess. So this ammonia in excess attacking the positive center here, repelling electrons towards a nitrogen. There is heterolytic fission. The hydrogen now comes and benefits from this lone pair of electron. An amine is formed. The lone pair of electron, hydrogen benefits, plus the bromide that was in solution, all combined to give this structure, and that is why ethylamine is our final product. Thank you, learners. Thank you for listening. Thank you for listening. Please share, like, and most importantly, please help to subscribe. Thank you once more.